hope that I'm going to close. Tell us a little noisy. Around there, yeah. Tony Hoare won the Turing Award there, and there's a kind of pithy quote from what I found here. If you got the chance to read that while you're filling out the name tag. There we go. Maybe just did it right. So, all right, this is a gentle introduction to Hoare logic, and the second half will be a brief excursion into the COC implementation. So I am Steve. Oh, sorry, that wasn't the. I was introducing. This is Marianne. So the emphasis for our portion will actually be in chapter 1, and we kind of did a little. So there wasn't too much repetition, because we'll mostly be on chapter 2. Okay, let's go. All right, so first an overview of what we're going to be having for the presentation. So the first is we'll start off with some motivating examples about what's Hoare logic and what it's used for. And then we'll give some formal definitions. But these are just going to be mathematical definitions. I will show a little bit about how you could implement it in COC, but mostly that'll be in the second half of the presentation. There's sort of 6 core rules that we're going to be focusing on. Then I will wrap up my portion with putting these rules together to give some sample proofs of correctness. And then the final part will be on the COC IDE. All right, well, let's launch into it. So, my question to you guys is, let's look at this program right here. And my question to you is, will this crash, or maybe will it get into an infinite loop? I'll give you guys a second to look at it. So guys, any opinions on this bit of code? Do you think it could crash or get into an infinite loop?
I don't know why it would get into an infinite loop.
Ah, good. Well, it was a trick question, because it very well could get into an infinite loop. So go ahead and click. You actually know what you know, because maybe it's going to crash because it's Java code, and this is just one big syntax there, right? Or maybe it's a weird language where this right here is the command 10 go to 10. I didn't expect you guys to think of that, right? So that was sort of a trick question just to get you warmed up, right? That's my sense of humor. So go ahead and click. All right, so no more trick questions. Suppose this really is Python code, because that's the intention. Okay. So my question is, there we go. So the question is, does this crash? Or could it crash? Here it might require a little bit of Python knowledge. Okay, go ahead. Go to the next one. So it turns out it depends on the input. This actually could potentially crash. So for those who didn't know Python, do you think this thing could make this crash?
Like a
character. Yeah, you could just enter in a character here. So int, when you can only recast things, everything that for input is done as a string in Python. So if you type 35 as a string, it will successfully recast that as 35. But if you type x, it crashes. It can't convert that into it.
Oh, wow.
So, all right, so go ahead and let's get to the moral of the story. So it turns out, for Hoare logic, all these things we're talking about, they're not going to happen. Okay? So for Hoare logic really only makes sense. We're going to go under the assumption that it doesn't crash, there's no infinite loops or anything like that. Because that's kind of what the type checking does. So all the Hoare logic really cares about is the output actually correct? That's what Hoare logic is going to check. So go ahead and click to the next slide. So let's look at this same program again. I didn't change the program. But now I want to know, is this program correct? So suppose that the output displays, that is worth 15 cents. So is that the correct answer? Did it get it right? Remember, what do you think for this code? If it ends up this was being displayed, did it get the correct answer?
It is possible that that answer is correct, because since we don't know the input there.
Exactly, we don't know the inputs. We go ahead and click. So in general, just knowing the output's not enough. We have to know what the input was too. All right, so go ahead and click one more. So, all right, suppose we know now the input value is 3 for num nickels. How is the program giving us the correct answer? So I put in 3, out's coming 15. Is that actually the correct answer? This one might be a little bit tricky. What's your name? I didn't see your name on the name tag there. What's your name?
Oh, Joe.
Joe. Okay. So Joe, is 15 the correct answer? If the user puts in 3, and this program outputs 15, did the program work? Okay. That's I lied when I said no more trick questions. Seems a little bit tricky. Go ahead and click. There's still no way to know because we don't know what the program was supposed to do. Okay. So if we're talking about Iranian nickels, which are worth 6 cents, pretending, then it's giving the wrong answer. Or, to be really extreme, what if this program was supposed to convert Celsius to Fahrenheit? This program is way off. You can't necessarily go by the name of the variables, right? So the moral, take a quick one more. So the moral of the story is, not only do we know the code and the input, we know what the intended output is to say whether the program is correct. So now I think we're ready to formalize what a Hoare triple is. Go ahead. So here's what we mean by saying a valid Hoare triple. So it looks like sort of double braces P, and then C is some bit of code, and then we have the double braces Q. And the idea is that P and Q are true assertions about the state. And this is the precondition P, and it's something that's true about the state just before you hit C. And Q is an assertion about the state after C is done. So what should come out? So we say this is valid if it actually does happen. Okay, go ahead and click. So here's an example of a valid Hoare triple. So we've got, before it hits this line, I took away the whole input part. So we're just going to focus on this line. It says the sense worth is 5 times the number of nickels. We started just before hit the line with the number of nickels equaling 3. And we're saying the intended output is that the sense worth should be 15. This is actually correct. This is what's going to happen. Go ahead and click. But what if we were doing the Iranian nickels? Then this program would be incorrect. Can you guys tell me what the corresponding, it would not be a valid Hoare triple, but what would the Hoare triple be for this code if we were actually supposed to be doing Iranian nickels and not American nickels? And the Iranian nickels are pretending they're 6 cents each. So this is what the Hoare triple would have looked like, but it's not valid because this doesn't actually represent the state that sense worth is in when this program's done running. The program would have 15, but it was supposed to have 18. So we can use this way. So the valid Hoare triples represent correctly working code, the invalid ones not correct code. Okay, so let's go to the next step. Oh, yes, forgot about this little aside. So this isn't going to be relevant right now until we get to the COC implementation. But one thing to note is that this thing right here is a different animal than this thing right here. Okay? This right here is actual Python code, whereas this is us talking mathematically about the state that the program is in. So this is not Python code. So this is what we're going to be using to talk about this. So when we actually get the COC, this right here is in. I guess technically it's COC, still COC, right? But it's COC's version of running programs. And then this right here will actually be states. Okay. I'll actually pause for 1 second. Any questions about the definition of the Hoare triple? The intent of it? So you got some bit of code here. This is sort of I think it is sort of like some assertion about your environment. Right here before the code, and this is what it should look like after the code. Okay, let's go to the next slide. So, Miriam will do more of this when she actually is running the COG part of the IDE, but this is the definition of an assertion. So it takes your state and gives out some proposition. Now, when I'm writing it here, since I'm not writing it in COG, I'm leaving out the whole state part. Okay, so I'm not actually saying, oh, evaluate x in this state. I'm just going to say x is bigger than 5 or whatever. And this is the official definition of a Hoare triple. So, and then here's the notation for it. So the notation is just what I've been using. Okay. And the idea here is that P and Q are assertions, or assertion number, just a proposition about a state. And C is of type com. And actually, go ahead and do one more click. So this is just a reminder of the int commands that we have. So these are your basic in commands. So skip, assignment, forming a sequence of things, a conditional if, and a while. And it turns out we're going to end up with 4 rules for each of these. Just to back up for 1 minute. So in this definition, basically this reads just like I was describing before. It says if C starts in some state and then ends up in state prime, and then P is true in this. So you've got this, and you also have that P is true in the state. Then Q is true in state, and then up with that for C. Okay. Alright, so for each of those commands, let's talk about the OR rule that's going to help us deal with it. So the first one is assignment. So let's just say we have a single assignment that remember that the shortcut notation for assignment is : equals, because that means we're actually in int. It's not just the regular like Python way of saying it. And just as an example, suppose we want x to be 5 to be the case at the end when we're done. Okay. So in other words, if I write as a Hoare triple, it's like this is the statement of the code I'm running. X gets the value of I, and in the end, I want x equal 5 to be a true assertion about the state. What would have to be true before we hit this line? You guys tell me, I want this code to be correct. So if we get valid Hoare triple, what does P have to assert of the statement?
I equals 5.
Good. Yeah, go ahead. Good. So this would be a valid Hoare triple. And we can generalize this idea. Okay. So this is how we're going to make statements about Hoare triples with assignment. So whenever you've got x assigned to any arithmetic expression, and you've got some post-condition Q, how do we figure out what the precondition had to be? Well, we looked at the x's that were here, and we replaced it with y. Well, in this case, we're going to replace it with a. So go ahead and click. And they use kind of a goofy notation for this. So I'm actually not going to use this notation, but Miriam's going to have to when she's doing it. So it basically looks like this. You could think of this as being the substitute. It's not really doing a text substitution, because you actually have to sort of substitute after you evaluate here, but it's basically this is the idea. Okay, let's go to the next rule. So I call these the consequence rules. So again, here's just a bit of an example. So suppose we know that before we start running the code, that x is bigger than 3 in our environment, in the state that we're in. So, and we want to end up, or we end up with Q. So we know this is a valid Hoare triple. So when x is bigger than 3 and we run this code, we definitely end up with Q. What I want to know is, what about this? Is this a valid Hoare triple? What do you guys think? Okay, so I saw you nodding and I saw you shaking your head. So why don't we start with Linda? So why do you say it's not necessarily true?
Because x can be bigger than 3 but less than 42.
I agree, that could happen. However, remember, I'm wanting to know, is this valid? Which means this is for sure the state before we hit C. So x is definitely bigger than 42. The question is, are we going to have to cheat from that? Actually, kind of the other direction. So we know this is valid. The question is this valid? Well, if x is bigger than 42, that means for sure x is bigger than 3. Then we know this. That means we'll end up with a state Q, and assertion Q is true about the state. Therefore, we do have that. So it turns out this actually is valid. Now, how can we generalize this idea? So in general, we can take any precondition and weaken it, and then it will still be a valid Hoare triple. So go ahead and click and shows saying this in talk. So say if you know you've got some code here, you're going to end with the state Q, and here you've got this P prime. Someone's the same state. I don't need assertions about this. Sorry. So here you have P prime. Well, if we weaken this and say, oh, well, if we know that P, we have to use this weird symbol for implies, because remember, we're not dealing with the actual propositions themselves here. So you need the state here too. But the idea is that if you could somehow get from the propositional part to get to P prime, then in fact you could just weaken it and say, oh, that must be that we start with P. We have Q. Does that sort of make sense? Just intuitively, right? So if we've got P, and we know that, oh, P gets P prime, and we know P prime will end up after C and gets to Q, then the center. All right, go ahead. So this gives us a way to modify the precondition. How could we modify the postcondition? Can we weaken the postcondition and still have a valid for triple? You guys are shaking your head. So yeah, what would we have to do to get like a analogous rule where we change the Q?
Strengthen the postcondition.
Exactly. So that's really good. So technically in COT, they split this up as two separate rules. I think it was kind of being the same thing. I just call them the consequence rules, but technically we actually do the COT rules will have to identify which one we're using. But basically, it's just what G was saying. So if you've got ending up with Q prime, but you know that Q prime can get you Q, then we're going to have this. And again, you could logically it makes sense. This is reflecting correct program code. It's reflecting what we want to have happen, right? But all these things are actual theorem and COT. We can actually prove this. And intuitively, it makes sense, right? Because what's that? So if you just look at this, we want to establish this. So we know if we're starting with P, and we execute the code C. Well, according to this, if we start at P and execute C, we know we end up with Q prime. Oh, but Q prime implies Q. So therefore, the assertion is okay. That's fast. So this rule, I didn't bother with any examples for this one because it seems relatively straightforward, but let's go ahead and take a look at it. So we also have the sequence command in INT, which their shortcut notation for it is to do 2 semicolons. This is the idea. This is how we would build up programs, right? So we've got some commands and some other commands. So this together is one INT command. It's a bunch of ones strung together. In this case, just 2. So if we want to show the validity of this triple, so we know we started in state P, we do this code snippet C1, immediately followed by the code snippet C2, and we end up in Q. If we want this to be true, if we want to establish this, what 2 things do you think we would have to hold in order to get this? So I want a rule that lets me conclude something about the sequence. I want a rule about this. So what hypothesis do you think I'm going to need? What do I have to have in order to get this? So let me break it down a little bit more. So something just about C1 and something just about C2.
That C2 has to follow C1?
Well, C2 by itself might not inherently have anything to do with C1. Like one could be, some if statement or something, and the other one could be some assignment, and they might not necessarily interact with each other.
So, then the ending state of C1 is the starting.
There you go. Exactly. I go ahead and click. So here's what we need to have. We need to have that. So this is going to have to start with here. So we start with state P, and then do C1, and end up with some assertion R about your state. Sometimes they state that state. R. And then, C2 will take R to Q. So if you have both of those, then it makes sense that, all right, from starting with P and doing C1 and then C2, we'll get Q. Makes sense? Okay. Now, one thing that's in practice a little bit tricky, and we're going to see when we do some examples, is coming up with this R. It kind of materializes out of nowhere. So, all right, let's go ahead. So now we've got our rule about conditionals. So we want to show the validity of this. So we've got an if-then-else statement. So remember, B is some sort of Boolean expression. This is actually an int. That's the type for B. We've got some command here, some command here. This fi is just ending if loop here. So we want to get, we started with this P, end up in the assertion about the state Q. What 2 things do we think we need in order to be able to conclude this? Something that doesn't have if then else. We want to come up with this idea. We have to break it down to something with the C1 and C2. That's a little bit tricky. So what would we have to have true in order to say, yes, we have this for triples? So now we have a way of saying something with for triples with if then else.
Well, I want to try.
Okay, sure.
So the ending state of B is the starting state of C1 and C2, and And the ending state of C1 and C2 is Q.
Good. So the ending state for C1 and C2 have to be Q, because we don't know which branch we took, right? So it all sort of depends on, well, what are the options for B in the end when you get the value of B? What are the options for B? It's either what? Right, so yeah, so it's either true or false. If it's true, then we're going to do C1. If it's false, we're going to do C2. But either way, it better end up with Q. So I'll go ahead and click. So I think we're pretty close to getting it. So basically, these are the two things we need to know. Now, I'm doing a little bit abusive with my notation here, saying it like this, but I think this is the idea, right? So what needs to happen is we need to know that before you do C1, that you have P, oh, and B is true. Oh, in that case, you'll get Q. It'll be in state Q. Q will be true about the state that we're in. On the other hand, well, what if B is false? Well, if we're in the state where you have the assertion for P, but you also have not B, then we know that when you run C2, you also have to end up with Q. So if those two things happen, then we can actually include this thing about the substate. Does it make sense? Question?
And these are two simultaneous for statements about the same if and else.
Correct. So I'm sort of going in, so in the forwards direction, we say, oh, we've established this and we've established this, and therefore we know this. Now, when you're trying to prove something in COT, you're going to end up with this as your goal, so that means you would have to establish both of these separately.
But they both have the same end state?
They do both have the same, they both have Q. Yes. They have the same end state. Because if these were different than Q, you wouldn't necessarily know which branch you took, right? So they both have to end up with Q. Okay, go ahead. Click. This starts to get a little bit now messy to work things out. Because like I said, I was sort of using the notation here by throwing this on here. This is more formally kind of what it looks like. Because you actually have to evaluate what B is in your particular environment. But yeah, this basically says what we were saying. So you've got some function that gets a state. Let's make sure P is true in that state, and that the assignment to B is true. This is the Hoare triple right here. So you've got this, C1 gives you Q. Similarly for C2, but with the not. And then from that, for these two things, you can include. Okay. So I think we've got one last rule, but this one I think is the trickiest. So, so technically there is one other command, skip, but there's kind of nothing to that, so I'm skipping skip. All right, go ahead and click. All right, so we need to come up with a rule about how can we come up with some sort of or triple statement when we have a while loop. Well, problem is we're not going to be able to conclude just this. Right? So why can't this, like logically, if we want the whole logic to actually represent program correctness, we're not going to be able to say, oh yeah, we have this. Because Q can't just be anything. And let's think about why. Because what if the B were to be false? So what happens in while loop if your Boolean thing that you're looking at here happens to be false? How many times does it execute C? Not at all, right? So therefore, nothing's going to happen here. So if we started off with an assertion about our state P, and we do nothing, there's no way we can end up with some potentially different Q, right? So in the event that B is false, what does the Q have to be? It has to be P. So go ahead and click. So you might think, all right, this is going to be our rule for how to do while loops. But we can actually do a little bit better than that. We can say something more about this P condition. Because we know a little bit more than P. Because if we think this is our code, C, this is our command, so when this is done executing, there's something we can say about the state that we're in, other than the fact that P is true. Because what can we say about P?
C is false.
Yeah, B has to be false, because if B were true, it wouldn't have finished executing this. So this is what we actually can say about the end statement. So not only do you have the assertion P, you also have about not B. But there's still more we can say about this. Because we can't just say, oh, this is our rule right here, because as it's stated right now, this is false. And we can't just say, oh, here's our rule, this is not going to represent program correctness. Because what if C did something that altered P? We can't just say, oh, this is universally true for all C and for all states, because, and for all assertions, because there could be some C that changes P, so P's not going to hold anymore. So we need to make our, go ahead to the next slide. So in order for this to work, in order to have a Hoare logic rule that involves while, we need to say that P doesn't get changed by C. So how can we write that as a formal hypothesis? Give me a Hoare triple that says that. Essentially that P is the loop invariant. And whatever assertions P makes about the state, that doesn't change. There's nothing in the code C that changes that. We come to the Hoare triple that says that. Say that. What do you guys think?
Start with assertion C,
Mm-hmm.
have the
Uh-huh.
and then the ending state is P and.
Oh, actually, we step there. Is just P is good enough. So go ahead and click. There you go. That's what you're saying, right? So you started with some assertions P about the state. We didn't see to it, but P's still good. It's still there. Okay. But it turns out we can actually do better than that. Okay. We can strengthen this hypothesis a little bit. So this is basically saying that, C didn't change P. Okay? But we can actually strengthen that precondition a little bit. Because think about what we're trying to get to. We're trying to say something about this while, and this is what it looked like. So what can we say, in order for C to get run at all, what can we say about B? It would have to be true. So let's go ahead and come on. This is actually sufficient. So we can say, all right, if you start with P and B and run C, you'll end up with P. Now, B still might be true, B might not be true. No, we don't know, okay? But from this, we can get this. We already mentioned P is the loop invariant, and I say, notice that even though C doesn't change anything in P, it hopefully changes B at some point. Because otherwise, you don't want B to always continue to be true. At some point, something's going to change about that B, including expression. Okay, go ahead and click. And yeah, this is just the statement in cock of what we just said. It's almost a direct translation. All right, so I think we're ready to, so we basically have all our core rules. So let's go ahead and click and try a problem together. Actually, originally I had a problem where I thought it was kind of cool. It was like subtracting 2, subtracting 2, subtracting 2 over and over again. And I wanted to show that the end result was actually the same modulus in mod 2 as the original. But it got a little bit more complicated. I was kind of concerned about time. So this one is actually fairly. Speaking of which, I will pick it up. So, so here's our program right here. So x gets assigned the value of x plus 2. Y gets the value of 3 times x. And I want to know if we start with x equal 4 in our starting state, will we end up with, well, I want to know if our goal is to get y equal 18, does this program accomplish that? So is this a valid Hoare triple? Well, it's not any of the, yeah. Good eyeballing it, okay. So using just the rules that we have, theoretically they can prove it on top. Okay. So what rule could we use to establish this? Because we don't know it's true yet. I mean, eyeballing it, yeah, it seems like it should be true. But using just the Hoare logic that we have, what rule would apply here to get us this? So remember that 6 Hoare rules are assignments, consequences, sequences, conditionals, and iteration. A little bit of a hint. For iteration, what kind of commands does it deal with? What's the command? The while. There's no while here. So, okay, so we're not going to use that. what does conditional have to use? If. Now, certainly not going to be there, so we kind of eliminated these down. So, can anyone think of a good rule we could apply here? So imagine we got something else, we applied it, and we got to this. So we're sort of thinking backwards. Like concepts now. Sequence. Good. Go ahead and put. Sequence seems like a natural start, because that's like the main thing that we're doing right here. So, if you go back and look at the sequence rule, it breaks it up into the C1 and the C2. And we still have the end part here, and the start part here, and the end part here, but there's that intermediate Q. Okay? So if we can find some Q and make this work, then we could get this. So let's just focus on the second thing, second term. So we still need to establish both of these. The second one is pretty straightforward. This one takes a little bit of work. This one we can do in one step. So if we focus on the second triple right here, what rule can we use to establish? So you have to give me a Q and say what rule you can apply to get this. Pretty close. What rule would it? If we had x equals 6 here, what rule would give us that?
Assignment.
Good. So we do want to use assignment, but remember how assignment works. So okay, give one click. So you guys are writing off the assignment. And, oh, the light here is not so great as we get to the end of the monitor here. So, for the assignment, don't look at this part yet. So, the assignment rule, what you actually have to have is not x equals 6, but 3x equals 18. It sounds almost the same, but remember, if you have 3x equals 18 here for Q, then the assignment rule says, all right, look at this, replace this by this. So we're replacing the y with its value. But that's what the q has to be. Q has to be 3x. But now we know what the q is, we come up over here, and we basically have to now just sketch this one. So we got this first triple. We know x equals 4. That's the assertion on our environment. We have x gets x plus 2. We need to establish 3x equals 18. Can we use the assignment rule on this? Oh, that's nice. Cool. Is it legal to use the assignment rule on this? Now remember, the assignment rule says we do a direct substitution in our postcondition, we get the precondition. And that actual assignment has to be this thing right here. So you have to be replacing this with this and like that. Unfortunately, we don't have that because these formulas are completely different. Okay, this has an 18, this has a 4. So unfortunately, there's no way to get an assignment to work directly. But can you go ahead and click the next slide? This is the last slide, I think. So the assignment rule is not going to work directly because there's not a direct substitution. So we think to ourselves, if we were going to use the substitution rule, what could we get from the substitution rule? What would this precondition have to be to use the substitution rule? Not quite x equals 4. Remember, the code says replace x with x plus 2, and then get this, something about x. Therefore, the precondition is definitely say something about x plus 2. Of that arithmetic expression. Right here. So we don't really have this yet, but if we were to use the assignment rule, what can we say? We can take this and replace it with that. So go ahead and click. So in the interest of time, this is what the assignment rule gives us. It says if 3 times this thing is equal to 18, this thing happens to be x plus 2. It says, oh, and now let x equal that thing. Well, then 3 times x equals 18. So this is what it has to look like. So we know this from the substitution rule. But we still need this. We still need this triple up here. So how can we go? We now know this. We still haven't proven this, but is there a rule that lets us go from this to this? These are almost exactly the same. What's the only difference between this and this?
That x plus 2. One is just using x.
Yeah, so the x plus 2 part, so everything is actually the same except for the precondition. Because it's not quite just the x plus 2, because this is a 3 and this one doesn't, right? So what's the rule that we have that says, oh yeah, you can give me a precondition? in this case it's not really weakening equivalence. Yeah, consequence of right? So we know that if x equals 4, and that implies that 3 times x equals 2 equals 18. So you can use the consequence rule, the pre-consequence rule. Get that. Okay, how time-wise?
You said all your
I just said all the time.